Hi class. In this lecture today I want to talk about the distribution of the sample mean. So we know that the sample mean is a statistic of some type. So what exactly is its distribution? Alright, we'll hopefully do a bunch of examples. We'll have it make sense. Alright, so there are two objectives today. I want to describe the distribution of the sample mean when the mean comes from a distribution that's already normally distributed, and then I want to describe the distribution of the sample mean when the original or underlying data is non-normal. Okay, so statistics such as X bar, and we've learned a lot of different statistics, are random variables since their values vary from sample to sample. So for example, if we were to look at the average height in our class and compare it to the average height in the classroom next door, the two averages would be different. Okay, so they are going to vary. Alright, as such they have a probability distribution associated with them. Alright, so in this chapter we focus on the shape, center, and spread of a statistic such as X bar. So what is the distribution of all the different X bars from a sample could be? Alright, so the sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from sample to sample of size n. Alright, so these are a few definitions. What I mean by that is if we were to take sample sizes of, say, size 20 and compare it to the average of a different classroom height of also size 20, all right, those statistics will vary a little bit, so we're interested in seeing what are they distributed like. And so the sampling distribution of the sample mean, X bar, all right, is the probability distribution of all possible values of the random variable X, all right, computed from a sample size of size n, from a population when it has mean, and I'm using m here for mu, and standard deviations, sigma. So I have the population's standard deviation with a capital sigma in here. Alright, so here's what I want to do. I want to illustrate what I mean by this by doing a couple things. So I want to obtain a simple random sample of size n. I want to compute the sample mean. And then assuming we are sampling from a finite population, alright, repeat steps 1 and 2, we have a simple random sample of size n, alright, have been obtained. So repeat, until all simple random samples of size n have been obtained. Alright, so here's what we'll do. We'll describe the distribution of the sample mean from a normal population. Alright, here's our example. So the weights of pennies minted after 1982 are approximately normally distributed. So all the pennies in your pockets, okay, on average they weigh 2.46 grams and they have a standard deviation of 0.02 grams. Alright, approximate the sampling distribution of the sample mean by obtaining, so here's what we're going to do. We're going to obtain 200 different simple random samples of size 5 from the population. Right? And then for each of those sample sizes of size 5, we're going to compute the average. All right, so the data on the following slide represents the sample mean. All right, so the average weight of the 200 simple random samples of size n equals 5. All right, so for example, the first sample of size n equals 5 had the following data. So we got 5 pennies. And here were their weights: 2.493 grams, 2.466 grams, 2.473 grams, 2.492 grams, and 2.471 grams. All right, so if we look at that, the average of those is 2.479. So now just going back, notice how that sample of 5 was different from the population average, what we thought it would be. And that makes sense, all right, because it's a sample, it's not going to be exactly right because it's only 5 pennies. All right, so here this slide contains 200 averages. All right, so each one of these values is an average of size from a sample of size n is equal to 5. All right, so we know that the mean of the 200 samples is 2.46. All right, so this is the same as the population. So the way I like to think about this, all right, the average of the averages should be whatever the population average is, and that makes sense. All right. So the standard deviation of the sample mean, so if we looked at all these values and just computed a standard deviation from them, all right, it's 0.0086. Notice that's smaller than the standard deviation of the population, all right, because the standard deviation for the population back here, all right, that's for all the pennies, all right. This standard deviation is the deviation of the averages. So since it's not all the pennies and it's just averages, it should be smaller. All right, so then next, suppose I took these 200 weights, or 200 averages, excuse me, all right, and we learned how to show it as a histogram, like we want to summarize this data. Well, the next slide shows that. So this is the frequency histogram, all right, of all the different sample averages. Well, what does it kind of look like to you guys almost? Well, to me it looks almost like a normal curve. Not perfect, but it looks an awful lot like it. All right, so what I'm saying here is it looks like the distribution, you might want to write this down in your notes if you have them handy. The distribution of the sample means looks like a normal distribution. Huh, that's crazy. We're saying a statistic itself follows a normal distribution. All right, so what role does the sample size n play in the standard deviation of the distribution, so the variation? All right, so here's the thing. As the size of the sample increases, the standard deviation of the distribution of the sample mean decreases. So as your size goes up, your deviation goes down. You want to know why? Because as the size goes up, your estimates get better and there'll be less variation in them, so the deviation goes down. All right, so to illustrate this, let's approximate the sampling distribution of the sample mean by obtaining, again, 200 simple random samples, but this time our sample size is going to go from 5 to 20. All right? And this is again from the population weights of pennies minted after 1982. Well, if I do that, okay, so this is a little different. Now I'm just going to give you the histogram, okay, of the 200 samples. Well, if you look at this, wow, this looks so much better than the previous one. All right, the mean of the 200 samples, okay, and this is their size is 20, is still 2.46. So the average is the average of the population, which is what we would think. But the standard deviation is now this. Whoa! It went from 0.0086 to 0.0045. All right, so as expected, there is less variability in the distribution of the sample mean when you have 20 compared to when you have 5. And that's because your averages are getting better and better and better. Okay, so we can now describe what the mean is and what the standard deviation is. All right, so the mean and standard deviation of the sampling distribution of X bar. Suppose that a simple random sample of size n is drawn from a large population with mean mu and standard deviation sigma. All right, like the pennies. So the averages for the pennies was 2.46, and their standard deviation, let me go back, forgive me, was 2.02. Okay, so we're drawing from a population that has average 2.46 and standard deviation 0.02. Okay? So the sampling distribution of X bar, all right, so the distribution of all the different averages, all right, we'll have a mean, so we say mu sub X bar. So this is the average of the averages. Well, that's just equal to whatever the population average is. Like if you look in the previous slides, we saw that the average for each of those histograms was always the same as whatever we thought the population average was, which was 2.46. So our standard deviation then of this histogram, of this data set, all right, we denote sigma sub X bar, so that's the standard deviation of the averages. Well, all we do to find that is we take whatever the population average is and we divide it by the square root of the sample size. So like if there were 5 pennies in each sample, that would go here. If there were 20 pennies, that would go here. All right, so the standard deviation of the sampling distribution, this thing, all right, we call that the standard error of the mean. All right, standard error, and is denoted sigma sub X bar. All right. We call it the standard error because if you think about it, standard deviation of the sampling distribution of X bar is a mouthful. So we call it the standard error. All right. So here's the shape of this distribution. So if you look at this, this was a normal curve. Turns out if a random sample X is normally distributed, all right, well then the distribution of the averages will also be normal. And we saw that in the histograms. All right. So let's do an example. All right, the weights of pennies minted after 1982 we've been using are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 grams. So here's just a question. What is the probability that a simple random sample of 10 pennies minted after 1982 we obtain a simple sample mean of at least 2.465 grams? So it's a little bit higher than the 2.46. Well, we know X bar is normally distributed. So its average, all right, the average of the distribution of X bar will be the same as the population average, which is 2.46. And we compute the standard error. Well, we take the population standard deviation, which is 0.02, and we divide it by the square root of 10. Like if you look here, we obtain 10 pennies. All right? So that turns out to be 0.0063, which is less than the 0.02 from the population. Well, whenever you're asked to compute a probability and something's normally distributed, you do a z-score. All right. Well, if you calculate the z-score, you take 2.465, the value you're interested in, you subtract away the mean, divided by the standard deviation, you get 0.79. Well, that's a shaded to the right problem. So the probability that you get a z-score greater than this is 1 minus, if you look up 0.79, you get this area. So the probability in a random sample of 10 pennies will result in an average greater than 2.465 is 0.2148. Okay? So let's, and if this seems a little bit confusing, we're going to work a bunch of examples in class coming up, I promise. All right, anyways, objective 2. Let's describe the distribution of a simple mean. This is from a non-normal population. All right. So the following table and histogram give the probability distribution for rolling a fair die. So when you roll a die, 1, 2, 3, 4, 5, or 6 could come up. Here's the relative frequency of each, or the probability you roll a 1, or probability you roll a 2. If you look at the histogram of that, here are the numbers on the die, here are the corresponding probabilities. The distribution histogram does not look like a normal curve, it just looks like a rectangle, so it's non-normal. Well, notice that the average here of a die roll is 3.5. We've done that. That's the expected value. We've done that in class. And the standard deviation is 1.708 for this. All right, so not normal. All right, so here's what we're going to do. We're going to estimate the sampling distribution of x bar by obtaining 200 simple random samples of size n is equal to 4. So here's what we're going to do. We're going to roll the die 4 times, and we're going to add up the numbers that we get and divide by 4 and get the sample mean, all right, for each of the 200 samples. All right, we're going to repeat this, all right, the same thing. We're going to do it 4 times, and then we're going to do it 10 times, and we're going to do 30 die rolls. All right, so histograms of the sampling distribution of the sample mean for each sample size are given on the next slide. So this is when we roll the die 4 times and get our average die roll. Then we roll it 10 times and get our average die roll. Then we roll it 30 times and get our average die roll. Well, so this is the average of 4 die rolls. Well, look at that. That looks almost normal. Looks pretty good. Well, now we do it 10 times. Wow. Now it looks even more normal. I bet when we do it 30 times, we're going to get an even better looking histogram. Wow. Look at that. If we rolled the die 30 times and calculated its average, all right, we get an almost perfect normal distribution. Look at that. So we started with sample size 4, 10, 30. As we increase the sample size, it looks like our non-normal population, well, the distribution of the averages becomes normally distributed. Wow. All right, so here's some key points. The mean of a sampling distribution is equal to the mean of the parent population, and the standard deviation of the sampling distribution of the sample size is sigma divided by the square root of n. And this is regardless of the sample size. So very important class then, the central limit theorem, or excuse me, very important theorem then. The central limit theorem says the shape of the distribution of the sample mean becomes approximately normal as the sample size n increases, regardless of the shape of the population, which is what we saw here. As we increase our sample size, the distribution becomes more normal. All right, so let's just do a couple examples real quick. Suppose that the mean time for an oil change at 10-minute oil change joint is 11.14 minutes, so they're actually not a 10-minute oil change, with a standard deviation of 3.2 minutes. All right, it's 2 parts. A, if a random sample of size n is equal to 35 oil changes selected, describe the sampling distribution of the sample mean. Well, x bar is approximately normally distributed, all right? Because as the sample size increases, all right, the distribution of x bar becomes approximately normal. The average, all right, well, the average of the distribution of x bar is whatever the population average is. And the standard deviation is, well, you take whatever the population standard deviation is, divided by the square root of the sample size. So divided by the square root of 35. The next question, if a simple random sample of size n, 35 oil change selected, what is the probability that the mean oil change is less than 11 minutes? Well, when something's normally distributed and you ask a probability question, that's a z-score and you look it up on the table. So it's 11, that's the value we're interested in, minus the average, 11.4, divided by the standard deviation, which is what we found. Well, that is negative 0.74. So you look that up on the table, on the z-table. The probability that you get a z-score less than negative 0.74 is 0.23. So there's like a 23% chance that your oil change at this place will be less than 11 minutes. All right, class. We will pick this up next time during our in-class lecture, and we're going to work a ton more examples like this. We'll talk about how you calculate the mean, the standard error here, and we'll do a bunch of z-score problems. All right, thanks, class.